We have been talking about inference for a population proportion, and surely you had to know that eventually it would come to this, that we need to find a confidence interval for a population proportion. Everything that we have been talking about up to this point has been leading to this moment. What you're going to be using when you conduct inference for a population proportion is a confidence interval. So in the previous videos, I was helping you understand what lies beneath the construction of this confidence interval. Now it's time to actually do it, and there are two methods we can use. The first method is to hypothesize a value for the population proportion, use the sample data to estimate the proportion, calculate a z-statistic if we have a hypothesized population proportion, pi sub 0, and if we estimated the proportion, p, and if we know the sample size, n, we can calculate the z-statistic. And then we use the z-statistic to test the hypothesis, comparing the z to critical values, or better yet, calculating a p-value. And then we repeat, and we repeat again, and we repeat again. And we keep putting in different values, different guesses for the population proportion until we have guessed every possible population proportion. All of those that are not rejected will be in the confidence interval. The confidence interval consists of the hypothesized population proportions that we retained. Obviously, this is going to require us doing many hypotheses tests. There's an easier method. That's method 2. Use the sample data to estimate the proportion. Use the normal distribution to find the z critical value. Calculate the standard error. Calculate the margin of error. Margin of error is always critical value times standard error. And then construct the confidence interval. Here's the formula. Z star represents the critical value. P is our sample population proportion. N is again our sample size. If we take the standard error, P times 1 minus P divided by N square root, and multiply it by the critical value, that's the margin of error. If we add and subtract that margin of error from our sample proportion, we end up with the confidence interval. Let's see how to do this using R. I'm going to use the same study that I referred to earlier. A study that was published in the Journal of the American Medical Association in 2012 reported that 319 out of 418 individuals who had gastric bypass surgery maintained at least a 20% weight loss 6 years after the surgery. To build a confidence interval, we can keep testing various hypotheses and collect all those that we do not reject, but there's a better way. Let's just calculate the margin of error. I'm going to use these data from the gastric bypass surgery. Here's the sample proportion. That sample proportion is 0.76. About 76% of the individuals kept off the weight for 6 years. Let's make sure we have a large enough sample size so that the sampling distribution of P will be normal. This time, we don't have a hypothesis, and so we're not multiplying our sample size by the hypothesized population proportion, but instead, we can use the sample proportion as an estimate. So that's what I'm going to do now. I get 319 when I multiply 418 times P, and I get 99 when I multiply 418 times 1 minus P. Notice something about these numbers. These calculations simply reflect that there are 319 that maintained weight loss and 99 that did not. So when you are collecting data and you are putting people in one of two categories, the number of people who are in each category can be used to see if you have met the condition that n times p and n times 1 minus p are both greater than or equal to 10. You can simply see how many responded in each category. Now let's obtain the critical value. The critical value is obtained from a normal distribution. When we were using standard errors and the mean, we used a t-distribution, but for proportions, you use the normal distribution. I'm going to construct a 95% confidence interval. That means that I need 0.025 in each tail of the distribution, so I'm going to look for an upper tail critical value by using Q-norm 0.975. And that critical value is a number that you're probably starting to become familiar with now. It's 1.96. Let's obtain the standard error. That's 0.0208. Now we can multiply these to get the margin of error. The margin of error for this study is 0.04. If I add and subtract the margin of error from my sample proportion P, I can get, by subtracting the lower bound, 0.72, and by adding the upper bound of 0.80. So what we have determined is if we look at the population of individuals who obtain this gastric bypass surgery, between 72 and 80% of them will keep the weight off for at least 6 years. Good news. Just as we had a function to create a confidence interval for the mean, there's a function in R to do all this calculation for us and create a confidence interval for the population proportion. That function is called prop.test. Now, prop.test can be used to test a single hypothesis. Why would we? But we could, if we want to, do it like this. We put in as the parameters for prop.test the number of people who were successful in keeping off the weight, 319, and by the way, it doesn't matter if you put in the 319 or the 99. We put in 418, the sample size, and then if we're testing a single hypothesis, we provide that hypothesis. In this case, I'm going to test that the population proportion is 0.7. We run this, and I get a p-value for the hypothesis test, but more importantly, I get the confidence interval from 0.72 to 0.80. If all I want is the confidence interval, and that usually is what I want, I just need to provide prop.test two parameters. The number of individuals in one of my two categories and the sample size. That's it. That's how easy it is. And it provides the confidence interval from 0.72 to 0.80. One final note. You'll notice in the title of the output, it says one sample proportions test with continuity correction. What does that mean, continuity correction? Well, notice that we're using categorical data. That's very discrete. We're either getting yes, no, 0, 1, success, failure. We're using categorical data with two categories. But what kind of distribution are we using in order to create the confidence interval? We are using a normal distribution. We're doing that because the sampling distribution approaches a normal distribution. The fact is, it's never quite exactly normal. Statisticians had figured out a way to make our confidence intervals just a little more precise, and this method is called continuity correction. We don't need to know what goes on behind the scenes to make this little slight adjustment to our confidence interval. But I am letting you know that that adjustment is in there. There is a way, if we wanted to shut that adjustment off, to run the prop test with the continuity correction shut off. But I see no reason for that. I like the fact that mathematical statisticians had figured out how to make my confidence interval even a little bit more precise. So that's what I'm going to use. I now have the data I need. I now have inference for a population proportion. And with that information, we can end this series on making inferences about population parameters.